So the second topic that we're going to be touching on today, we're not going to have time to do it full justice, is the issue of sensitivity analysis. We've seen how stochastics yield uncertainty in model output, but there's often broader uncertainties associated with a model. We may have put data into the model that we're not sure about. There may be aspects of model structure in which we lack full confidence. There may be certain assumptions we've captured with this model in terms of how things progress, for example, that we're really not sure about. And there's a lot of uncertainty about how things work in the world. And I argued early on in the class that these models are thinking tools. They help us investigate at a concrete level the operational implications of our assumptions about different hypotheses concerning how the world operates. They let us say, well, suppose things were kind of like this. What would the implications be in terms of the data we'd expect to see? How consistent is that with what we see? Suppose they're this other way. So, the models are not predicated upon. They don't posit. They don't rely upon. They're not contingent upon large amounts of sureness in the data. In fact, sureness in data or sureness in model results. In fact, they help us reason through the significance, which may be large or small, of uncertainty. And a key part of that process is performing sensitivity analysis. So here we're taking a model and we're seeking to understand in a systematic fashion how its results will vary as we change assumptions about the model. Now, these assumptions may be assumptions about parameter values, or they may be assumptions about the structure of the model. What thing is connected to what thing? What, for example, the structure of a state chart. Or, what transitions go out of a given state to other states? Is it possible that you can lose your immunity after gaining it, for example? Is it possible that some people are lost their immunity, going back to a susceptible state? That would be more of a structural sensitivity analysis. And there's many ways we can conduct these. We can examine the impact of changing individual variables at a time or multiple variables at a time. We can examine systematically one set of variables after the other. We can draw variables from distributions. Marlow analysis. Excuse me. In general, we can also examine the impacts of stochastics. We just saw some of this, or static uncertainty. So, when we're trying to capture the impact of model uncertainty about this model, whether this model is suitable, we're often changing our assumptions. We're examining the impact of changing our assumptions about how the system works. So we might vary explicitly the structure of the model and see the impacts and outputs. Now, sometimes we can do that more easily than others. For example, for a transition. Let's suppose we had a transition from what we saw in the very first class where we used AnyLogic, right? We actually added a transition. Do you remember that? Between a recovered state back to a susceptible state. Do you remember that? And that triggered these waves of infection, right? Suppose we're not sure if that empirically, if that exists. Does that really exist? How might we change only parameter values, but actually see what the impact would be of assuming such a transition or not? Well, in AnyLogic, we might make that transition guarded, for example, on a parameter. Right? It only can fire if a certain parameter is true. Or we make it occur at a certain rate, and the rate could be 0 in front of some of our simulations. So that's kind of functioning as kind of a structural sensitive analysis in the sense that we're totally blocking off that whole transition. But there's other ones which we might not be able to examine as nimble, as agile a fashion. For example, sensitivity analysis where we might change the number of states in the state chart. That would not be as easy to do. In fact, it would be considerably harder to do using built-in state charts. Here it often involves somewhat more work than some of the techniques we'll be talking about. We're going to be, I think with predictor corrector models, I'm actually going to try to give a lecture on this later if I have time. But the idea here is that we may examine the impact of having some uncertainty about the model itself and some uncertainty about the data, and we fuse them together to yield the best consensus estimate going forward. So we know our model's imperfect. How many people here, well, I think everyone in the room here lives, somewhere near the city. How many people think that they have a very good mental model about how to get home from here? Yeah, hopefully it's most people in the room. How many people, could, with great confidence, go home using that route with your eyes closed? Okay, maybe. How many people believe they could get home alive with their eyes closed, having attempted that? So the fact is there's a lot of things in the world where even if we have a very good understanding, a very good model, mental model, computational model, describing something, expecting perfection from it is often too much. There's a lot of factors in the outside world, the vagaries of temperature and rainfall and economic activity or what have you, that we're just not going to capture realistically. It's not going to capture. But the fact is the model can still be incredibly useful, incredibly valuable. And what you need to pair it with is a bit of observation. Right? You need to pair it with just a little bit of observation. And those of us who do know the drive home very easily, probably we could walk home reading a book, with occasionally looking up from the book, or, well, these days, I show my age, we could walk home with one of these, right? And I could do so with only occasional checking of my bearings, right? Just look up occasionally or just sort of check out the ground in front of me. I know where I is. The point is I'm constantly getting new input to just double check my model, right? And that input is fallible. I may not notice certain things, etc. But combined with my, based on that input alone, and without any clue about how to get home, I wouldn't be able to get home. Based on my mental model going home with my eyes closed, I wouldn't be able to get home with confidence, certainly not alive. But combine the two. Good mental model, frequent updating from, just on an occasional updating, even rough. You can combine the two and get something very powerful. Something will get you home with great confidence every single time. So really that's the idea behind these predictor corrector models. It's, and the beauty of it is even with a very imperfect model, a very rough model, you can get a lot of value out of it by just combining it with new observations when they come in. You can with great confidence project forward, at least in the short term, because you've captured the essential regularities. You've captured the essential features, but you would never look to it to guide you, as we say, open loop in the long term, right? So it turns out these models can be very nicely implemented in AnyLogic, but that's a subject for hopefully a later lecture. Okay, there's certain types of analyses, which I'll call static uncertainty analyses, where we'll seek to investigate the assumptions of seek to investigate the outcomes or the consequences of different assumptions by varying things one time ahead of the model, and then we run the model and see the consequence. And we try again with a different set of assumptions. So we run it again and see the consequence. So they identify, for example, initial values of parameters or initial states that have really big impact. And we may find for our outcome of interest that with respect to certain of the model variables, and this is just to show this type of diagram, you know, a 10% difference in one model variable might make a big difference in the outcomes of interest. A 10% difference in another model variable makes a very small difference for sort of the typical case we're examining. And we can draw it out in different ways. With this model that we're looking at, I'd like to actually undertake one of those. So let's go take this model, and I'd like you to, again, open up this experiment called Monte Carlo 2D histogram. And I'd like you to go up here back to this screen, this general area of it. And instead of saying this sort of free-form variation here, what I'd instead like to do is to have a varied in range here. And I'd specifically like to associate the average illness duration, instead of with a fixed value of 15, go to between 5 and 25 step size of 5, okay? So to do that, we have to change this from a fixed to a range, and then we can do it from 5 to 25 with a step size of 5, okay? Now, by the way, this will be helpful for your problem set. Okay. This exact operation, I think, is one of the things you're called upon to perform in your problem set. Okay? So now I'm basically saying, you'll notice it grays out the number of runs. Why does it gray that out? Yeah, it knows how many it has to run through, right? And that's determined entirely by this set of values here. You guys need about 5 to up to 25 with step size 5. It can't be simultaneously told how many runs. It's a given. Okay, so let's run that out. Okay, and let's see what results. So let's see what sort of variability results. Anyone want to guess? What do you think will happen? We're changing the average illness duration. We're successfully raising it from a very small value to a larger. What should we see?
Longer and taller.
Okay, progressively longer and taller. Very good. The longer people stay infected, the sort of longer it will take for the population to recover here. Remember, this is being drawn down by flows out due to recovery. And people are going to be in that recovered state for longer. And moreover, they're going to be able to infect additional people, so it's going to be going higher because they infect a cumulatively larger number of people over the entire course of their illness. Their effective reproductive number is higher. So we see this. And you'll notice, ladies and gentlemen, that for each of these, it seems to have run it just once. Let's suppose we wanted to run it not just once, but we actually want to capture the variability for each of those. Because after all, each of those was a run with a specific values of parameters. But we know from the past lecture that I just gave you that there's variability, even assuming the same exact set of values of the parameters. There's variability, is there not? There is. So let's go see how AnyLogic allows us to investigate that. Next to that distinction, ladies and gentlemen, that distinction that we saw in the last lecture between the experiment and the, I thought I had it in here, but I don't. The distinction between the experiment and the simulation, etc. Okay? Let's go do that. So this is ad-libbing a bit, but let's go click down here, and let's go down to replications. Replications dictate the number of realizations, the number of runs and reruns for each simulation, each particular assignment of values to parameters. So here, we're going to have an experiment. For that experiment, we're going to be running, what is it, six simulations, is it? And for each of those, right, 5. And for each of those, we have, we're going to be running a set of realizations dictated here by by this number here, this number 10. Okay, so for each of those, we're going to be running out a series of replications, of realizations, for the given set of parameter values, again and again and again. Okay, okay. So let's go see this here. And now we see some broad differences between the different runs, but we actually see there's a degree of variability here. So we're running this up, and you'll notice that there's a total of how many total simulations, or how many total runs made? 50. Why 50? 5 times 10. 10 so 5 simulations, each with a set of different values for the parameters, and then for each of those, 10 different realizations, right? And you can kind of see that they fall into certain bands here, right? I can actually see it very strongly on my screen. I don't know if you can see it on your screen. The screen up here kind of bleeds it out. But now we've seen now all 3 of those levels. Now we have an experiment. Remember, we used to have one experiment is one simulation is one realization. We run it, and that was the complete life cycle of the run. Now we have one experiment running multiple simulations of the model, each with different assumptions about the parameters, and then each of those running 10 different realizations. Okay, it's a lot more mechanism going on here. Let's temporarily turn that off, and we'll finish just with a with making this not just one parameter variation, but 2 that are varied. Ladies and gentlemen, I'd like to go down to the contact rate, and I'd like to change that to be the infection probability, and I'd like that to be changed as well, so that we have infection probabilities coming from 0 to 0.1 with a 0 to 1 with a step size of 0.1. Okay, so we go down here, infection probability, change this to be in some range, and we go from 0 to 1 with step 0.1. Okay? So now, ladies and gentlemen, what would you expect to see? Anyone?
The early ones won't take off at all, or they'll spike and then die off.
Good. Good. And the later ones?
Everybody gets it.
Okay. So the...
You're going to be 55 experiment runs?
Very nice. Yes, because I turned off replications. So 55. So 0 to 1, 11, and then 5. So 5 to 25, step 5, being the other 5, and very nicely done. So here, oh gosh, you can barely see it. The thing that dominates is what Kurt has highlighted. There's a lot that don't take off. But I can actually see, I think it'll be much better on your screens for those who have screens with them. But there's actually like one that goes way up here. A lot are clustered in this region, but then there are some that kind of go like this. And generally speaking, we get a wide range of variation, but the biggest, most dominant one, most pronounced one is this one down here, where it's not taking off. It's just probably petering out initially. But it's worth noting, some of this, like dark from here, could be from where? Not all of this is had all the way through. We're not looking here necessarily at longitudinal depictions that follow an actual trajectory. Some of these that are dark right after 140, for example, could have been runs that came up and then came down by this point. These are just histograms, and the number that fell into this bin. And some fell into the bin because they stayed low all the time. Others fell into the bin because they went up and died down. Others went up and died down over here and were still low by that point. So it's probably becoming somewhat darker here and somewhat lighter over here, which seems to be the case. Okay? So here we've examined a two-way sensitivity analysis. We've run this model, varying these parameters, 2 parameters at the same time in a grid gridded fashion. It's going through systematically and examining each combination with them and running the model for that. And I apologize it's so washed out. Next time, we'll be further examining some opportunities for sensitivity analysis, for example, drawing values from distributions, and we'll be then on to a subsequent discussion of calibration. We'll also talk about how to avoid the combinatorial explosion, or how to lessen it anyway, our vulnerability to it. When we have a bunch of parameters, how do we avoid running millions of these sort of runs for different types of assumptions? How can we wheedle that down? And there's some techniques that we can use to do that. Okay? Very good. So that's all for today. And see if you can get started on that problem set for some time in the coming week.